All right, whether you're an aspiring aviation student or just a massive aerospace nerd, let's dive right into this explainer on why and how carbon fiber composites are completely taking over the modern aerospace industry. I mean, if you look at any high-performance vehicle today, from the latest rockets to next-generation commercial airliners, carbon fiber is at the absolute forefront of the design. So today, we're going to unpack the science, the engineering, and the incredibly meticulous manufacturing processes that make this material the undisputed atomic armor of aviation. To kick things off, we really have to ask the ultimate question driving modern aviation engineering. Why on earth are we rapidly replacing century-old metalworking techniques? For over 100 years, aluminum has been the absolute go-to material for aircraft. And it's a great material, right? It's cheap, it's easy to manufacture, and we have a full century of experience stamping and riveting it. But metal has some distinct limitations. Over time, aluminum fatigues, it corrodes, and it just carries a lot of unnecessary bulk. That extra weight acts as a permanent penalty on an aircraft's fuel efficiency. And in the modern aerospace industry, efficiency is absolutely everything. Just think about this sheer multiplier. Carbon fiber boasts a strength-to-weight ratio 5 times greater than steel. This metric is known as specific strength. If you take a sheet of steel on a sheet of carbon fiber of the exact same weight, the carbon fiber is going to be 5 times stronger and practically twice as stiff. This is a complete paradigm shift for engineers. It means you can build an airframe that handles massive, multi-ton aerodynamic loads while weighing just a fraction of what a traditional metal airframe would weigh. Section 1. Cloth and Glue. Composite Basics. To really grasp how a massive airplane flies using this stuff, you first have to understand the chemistry. We're going to use a micro to macro building block approach here, starting at the very foundation of the materials. Think of aerospace composites as literally just high-tech cloth and glue, where the carbon fiber acts as the load-bearing reinforcement and the epoxy resin matrix locks those atomic-level fibers securely in place. By itself, carbon fiber is just a soft fabric woven from microscopic threads of carbon atoms. You couldn't build an airplane out of it any more than you could build one out of a t-shirt. But when you saturate that fabric with a specialized polymer matrix, like an aerospace-grade epoxy, and let it cure, the resin hardens. It binds the fibers together, transfers the physical load across the entire structure, and protects those delicate carbon strands from the harsh outside environment. And that brilliantly illustrates why we absolutely still need metal for things like 3D load-bearing bolts or extreme temperature zones like titanium firewalls, while carbon fiber rules the flat 2D aerodynamic surfaces of the airframe. Carbon fiber is incredible at handling tension and compression along the X and Y axes of its flat layers, but it lacks Z-axis strength. If you pull it directly apart, the layers can actually delaminate. Plus, the epoxy matrix generally limits its operational temperature to around 200 degrees Celsius before it begins to soften. So, engineers use carbon fiber for the sweeping 2D curves of the fuselage and wings, while relying on machined aluminum or steel for intricate 3D mechanical joints, landing gear, and high-heat engine exhausts. Section 2. Fiber Orientation and Strength. As we scale up, we get to see how engineers actually align these microscopic fibers to handle massive aerodynamic forces. This is where composites gain a huge advantage over uniform isotropic metals. Because carbon fiber strength is highly directional, engineers meticulously arrange fibers at 0 degrees to handle wing bending and at 45 degrees to endure intense shear stress. This is called an anisotropic material. Instead of just accepting the uniform strength of a sheet of aluminum, an aerospace engineer can dial in the exact strength they need, exactly where they need it. If the wing is going to be pulled incredibly hard from root to tip, they just lay down more layers of carbon thread at that 0 degree spanwise angle. If the wing needs to resist twisting, they overlay threads crossing at positive and negative 45 degrees. It's essentially structural programming. Section 3. Wing Structures and I-beams. So we've got our perfectly oriented fabric, but now we need to shape it to hold up an entire airplane wing. The really crucial point here is understanding the classic I-beam analogy, where the top and bottom spar caps endure the tension and compression of the bending wing, while the central shear web handles the vertical loads. When an airplane is in flight, lift pushes up on the wings, bending them upward like a giant diving board. This creates immense compression on the top skin of the wing and massive tension on the bottom skin. By forming our carbon fiber into an I-beam shape, we push the strongest materials far away from the neutral centerline. This places the thick spar caps exactly where those bending forces are the most violent, while the thin vertical web keeps the caps from collapsing toward each other. Now, when you compare a traditional foam core sandwich panel against a modern hollow grid design, the differences are wild. The hollow grid utilizes CNC automation to eliminate molds, drop 10% of the weight, and, get this, open up interior space for long-range fuel. Traditionally, composite wings were built around solid foam cores to prevent the thin carbon skins from buckling, but this required expensive, specific molds for every single part. The newer hollow grid technique cuts a cellular network of mini internal I-beams from flat panels using a highly precise computer-controlled router. It's incredibly automated, remarkably light, and here's the real genius of it. Because it leaves the wing mostly hollow, it acts as a massive built-in fuel tank. Section 4. Layups, autoclaves, and automation. But how do we actually turn these soft, sticky layers of carbon cloth into rigid, flight-ready structures? Well, it requires a crazy blend of handmade craftsmanship and intense industrial processing. This brings us to a meticulous production process, where pre-impregnated fiber layers are laid up, vacuum-bagged, and basically baked into stone inside a giant pressurized oven called an autoclave at around 250 degrees Fahrenheit. Honestly, think of it like the world's most stressful, multi-million-dollar easy-bake oven. First, technicians carefully stack layers of carbon cloth, often called pre-preg because it already has the exact right ratio of epoxy resin embedding in it, into a mold. Next, they seal the whole assembly inside a vacuum bag and suck all the air out. This atmospheric pressure crushes the layers together, completely eliminating microscopic air bubbles that could weaken the final part. Finally, inside the autoclave, extreme heat and pressure trigger a chemical reaction in the epoxy, permanently locking the atomic structure into place. Section 5. The building block validation. Here's the thing, you literally can't just simulate these complex materials in a computer and call it a day. We have to physically prove them. Metals are predictable. Carbon fiber is infinitely complex. So to ensure they won't snap mid-flight, the FAA uses a strict building block approach. They force engineers to break hundreds of small material coupons before scaling up to test subcomponents and finally, physically bending a full-scale wing to its limit. They start right in the lab, pulling apart tiny strips of carbon fiber to record the exact point of failure. That physical data is then fed into software to design larger pieces like ribs and shear webs, which are also built and pushed to the breaking point. This rigorous step-by-step physical validation culminates in a massive hydraulic rig bending the entire completed wing to its ultimate design load. It ensures there is absolute zero guesswork when human lives are on the line. Section 6. The Great Aerospace Trade-off. Alright, it's time to pull back and look at the macro perspective, the real-world aircraft and the massive engineering compromises involved in choosing composite materials. Because everything in aviation is a trade-off. When Boeing launched the 787 Dreamliner, they completely shocked the industry by building a commercial airliner whose structural weight is over 50% carbon fiber. While earlier planes had used fiberglass or carbon fiber for small fairings or tail sections, the Dreamliner fundamentally changed the game. The entire barrel of the fuselage, the massive sweeping wings, all constructed from advanced composites. It was a massive financial and engineering risk for sure, but the payout proved exactly why the industry is shifting away from aluminum. Because carbon fiber doesn't fatigue or corrode like aluminum, this specific aircraft achieves 20% greater fuel efficiency, slashes maintenance downtime by 35%, and even allows for a higher, more comfortable cabin pressure for passengers. The weight savings directly translate into massive fuel savings for airlines. Furthermore, aluminum weakens every single time it expands and contracts during flight cycles, requiring constant inspections. Carbon fiber? It's practically immune to that fatigue. That incredible structural strength even allows airlines to pump more air pressure into the cabin, leaving you, the passenger, feeling much less jet-lagged after a long oceanic flight. But, of course, there's a catch. There's always a catch, right? Carbon fiber is around 10 times more expensive than steel, and the manufacturing process is incredibly slow and labor-intensive compared to traditional, century-old metal stamping. It is a material that demands absolute perfection. A single speck of contamination or an autoclave temperature that strays by just 5 degrees can literally force an entire multi-million-dollar batch of aerospace parts straight into the trash. The overhead required to build the massive clean rooms and giant pressurized ovens makes this an incredibly exclusive manufacturing process. So, we've just unlocked the atomic-level secrets of aerospace's most transformative material. As automation makes this high-tech cloth and glue cheaper to produce, it's going to reshape far more than just commercial airplanes. For the aspiring engineers watching this right now, the sky is literally the limit. What will you build next with this knowledge? Thanks so much for joining me on this explainer, and I'll see you next time.